cord. Okay. Okay, electrochemistry is carried out in what we call an electrochemical cell. Does it have to be in an electrochemical cell? No. You can just throw everything in together and react. Do it all in one pot. But traditionally, it's done in a way that you take the two half reactions, the oxidation half reaction and the reduction half reaction. And you put all the components of the oxidation half reaction on one side. It's typically drawn on the left. All the components for the reduction half reaction, and you put it on the right. There's some terminology that you have to keep straight here. Okay, a couple things to say, ways to remember. Okay, the anode is oxidized. So the oxidation half reaction occurs at the anode, which is typically written on the left. And then you say the cathode is reduced. Notice anode and oxidized are both vowels, they stay together. Cathode and reduction, those are both consonants, they stay together. So you have the cathode side over here, and it has all components of the reduction half reaction. Okay, what that means is your starting material reducing agent is on this side. When the reducing agent is a metal, it becomes the actual electrode that's attached to the wire. And your strongest oxidizing agent of your starting material is over here. Okay, we attach a wire between the anode side that contains the reducing agent for the starting material. And we attach it and run it into the cathode side, which means that when the reducing agent in the starting material donates electrons, it's going to donate them to the oxidizing agent as the starting material, right? So this is the reducing agent, and the oxidizing agent is in solution at the cathode. What's going to happen to the electrons? The oxidizing agent is going to suck those electrons to itself. The electrons are going to flow through the wire and then react with the oxidizing agent that's in solution. Okay. If we attach a voltmeter over the wire, it will read a voltage. What does a voltage tell us? Again?
Current.
Related to current. Voltage actually tells you the strength of the electric field. So field. A field is a space through which a force acts. So you are in a gravitational field because gravity is acting in that field, right? And gravity is a directional force. It's only operating in one direction. An electric field, an electric field. If a gravitational field pulls on objects with mass, what does an electric field pull on?
Charge.
An electric field pulls on things with charge. And here we're talking about electrons with charge, right? So think about the fact the oxidizing agent has an attraction for electrons, right? And it's going to exert that attraction for electrons through the wire. So that the pull of electrons that the oxidizing agent has, because it wants those electrons, on the reducing agent. Sam said the voltage is related to the current, and it is. When you have an electric field or a voltage operating through a wire, what happens to electrons in that wire? They flow. So the voltage tells you something about the flow of electrons, how easily the electrons are going to flow from the reducing agent starting material to the oxidizing agent product. Okay. When the voltage is positive, you do need to know direction here. When the measured voltage across the electrochemical cell is positive, which way do the electrons flow? left to right. Okay, so if electrons want to flow from the reducing agent to the oxidizing agent, which way will the equilibrium lie? Like, which way is the reaction moving? Moving forward, yeah. So a reaction that's moving, an electrochemical reaction that's moving forward. Let's go back to something like this. If this reaction is moving forward, that means we take sodium half reaction at the anode, take chlorine reduction half reaction at the cathode. As long as the reaction is moving forward, that means electrons are moving from the sodium to the chlorine, right? Which means in an electrochemical cell constructed from this, the voltage will be positive. Here we have a different reaction. Same idea. As long as the E value measured in the electrochemical cell is positive, the reaction is salt rich thing.
Allow the reaction to move forward without disrupting charges.
Yeah. As electrons flow from one side to the other, you could end up with a buildup of negative charge on this side and a buildup of positive charge on this side. What will that do to the voltage? It will interrupt it, right? But if you pack a salt bridge with soluble ions, you allow them to flow from the salt bridge into the solution, the ions move to compensate for the transfer of charge from electrons. The reaction continues to its equilibrium unimpeded by any buildup of charge. So the salt bridge is just there to help the reaction.
On that last slide, would the flow of anions go towards the anode? Isn't that two like charges?
Okay, so when electrons flow from the anode to the cathode, what happens is you build up positive ions in solution here. So then to neutralize those positive ions, the new positive ions, you have negative anions coming from the salt bridge and entering. So it's just to keep the solution electrically neutral. Okay, so tell your neighbor what you know about electrochemical reaction or an electrochemical cell with that reaction when the measured voltage is positive, when the electric potential is positive.
That's what you must want to do.
So we know the reaction is spontaneous, or in other words, the reaction is wanting to move forward. So is it at equilibrium yet? No, it's not. Okay. Is Q less than K for that reaction or greater than K? Some of you are doing that. I've heard those words and I haven't thought about them for 2 whole weeks. Okay, if the E value is positive and the reaction is moving forward, that means we're to the left of equilibrium, right? Which means Q has to be less than K. We don't have enough products yet. Okay, what does that mean about delta G when E is positive? Delta G is negative when E is positive. So a positive electric potential for a redox reaction in an electrochemical cell is a kind of indirect way of just measuring the sign of delta G. When E is positive, delta G is negative. Okay, how about when E is 0? Does that ever happen? If we run this particular reaction long enough, what will happen? Come to equilibrium. When it's at equilibrium, will there be a net electric flow in one direction? When it comes to equilibrium, the starting material will stop being converted to product, right? It means electrons will stop flowing. So,
Yeah, maybe I have a break in understanding here, but if there's a salt bridge, how would it ever stop, come to equilibrium?
okay, so one definition of an equilibrium is when the concentrations of starting materials and products stop changing, right? So all the points up to equilibrium, what we're doing if we're moving in the forward direction is we're converting starting materials to products, right? For a redox reaction, that occurs with the flow of electrons. So when we come to equilibrium, we've stopped converting or stopped changing the concentration of starting materials and products. So overall, we stopped changing the concentration of starting materials into products. Which means what about the flow of electrons? It stops, which means what about voltage? It goes to 0. Yeah. So when E is 0, we're already at equilibrium. Okay. Is it possible to have a negative electric potential value? Yeah. What would that tell you about the flow of electrons? It's reversed. Okay, here's a question for you. In the anode, we have a reducing agent and an oxidizing agent product in solution. And then the cathode, we have the oxidizing agent starting material as written in the reaction in solution, and then we have a reducing agent product. If the reaction is moving forward, that means that the oxidizing agent at the cathode is stronger than the oxidizing agent at the anode. Does that make sense? Okay, if the reaction is running backwards because we have a negative E value, where's the strongest oxidizing agent? It has to be the oxidizing agent that's a product oxidizing agent in the reaction, which means we find it at the anode. There's lots of connections to make here. Okay, so E predicts the direction of reactions and tells us whether we're at equilibrium or not. Make the connection. What does that mean about unit 2 and unit 3? How does that connect to what we've done before? Delta G tells us the same thing as E. Okay, we actually have an equation, delta G equals minus NFE, where we could express that also. Similar relationship, delta G naught equals minus NFE naught. We'll talk a little bit more about that equation. Okay, it's a little tricky to always be drawing the electrochemical cell. And feel free to do that like on an exam. Map out the whole electrochemical cell. You also need to recognize that sometimes an electrochemical cell is communicated using shorthand. Okay, tell your neighbor how to read this. Where's the cathode? Where's the anode? Where's the salt bridge? What's the net reaction? What are starting materials? What are products?
Each side of the globe.
Yeah. They're just like the separation between. So basically.
One way to think about these dotted lines they are the salt bridge, which means everything to the left, that's your anode and your anode half reaction. And the reaction that occurs at the anode is solid zinc. So it's zinc 2 plus 2 electrons. So what's on the left is your starting material. What's on the right is your product. What's this line in the middle here? That's to distinguish between things that are in different phases. So in this case, zinc is a solid, zinc 2 plus is aqueous. So there's a phase change. One. Anytime you have something aqueous in solution, you have to say the concentration. So this is your 1 mole. Okay, everything to the right of this double line, that's the half reaction that's occurring at the cathode. So that's the reduction half reaction. It says copper 2 plus gains 2 electrons to form copper solid. And again, there's a phase change line in between, and anything that's aqueous has to have the concentrations given. Okay. We spend a fair amount of time in unit 2 and unit 3 asking you where will the equilibrium lie for a specific reaction, right? In units 2 and 3, what tools did you have to predict where the equilibrium would lie? So what thermodynamic parameters or symbols code for things that helped you predict where the equilibrium would lie in unit 2 and unit 3? K, right? The equilibrium constant tells you something about where the equilibrium would lie. Okay, there's also something else that tells you where the equilibrium will lie. Q versus K, or delta G naught tells you where equilibrium would lie. So remember, if K was greater than 1, equilibrium would lie to the right side of products, which corresponds to a negative delta G naught. If K was less than 1, then equilibrium would lie on the side of starting materials to the left. What kind of delta G naught would that correspond to? Positive delta G naught. Okay. Can we do same thing for redox reactions? Yeah. Yeah. Except we don't typically have tables of delta G naught values for redox reactions. We have instead E naught values, and we use them the same way. Okay. Conceptually, we think about the equilibrium and predict it the same way we did for acid-base reactions. So remind your neighbor, how did we predict if we had an acid plus a base that wasn't water? How do we predict where the equilibrium will lie? Acid-base reaction. The equilibrium can be seen as things competing to possess the proton, right? The base on the starting material side of the reaction wants to grab the proton and keep it. And if the reaction is moving backwards, that means the base, the conjugate base on the product side wants to grab the proton and keep it. So it's this competition for the proton between the bases, the base and the conjugate base. And if you can identify which of the bases is the strongest, you know which way the equilibrium will go, will shift. Okay, what's the corollary for redox? We're not competing for protons here in the forwards and backwards reaction. What's being competed for? For electrons. Okay, so what is it that's trying to grab the electron instead of, the base would grab a proton? What grabs the electrons?
Oxidizing agent.
The oxidizing agent. Okay, so we think about it exactly the same way. We say there's an oxidizing agent in the starting material, and there's a different oxidizing agent in the product. Whichever of those two oxidizing agents is the strongest will win, right? And the strongest oxidizing agent will grab the electrons and push the equilibrium to the other side. Okay, but here is the question. You have to know what's the strongest oxidizing agent. As a Chem 106 student, how do you predict or analyze to identify the strongest oxidizing agent?
The oxidation numbers.
Sometimes that will help you, but not always. E naught value, yeah. So just like for acid-base reactions, we had a table that ranked all the acids in terms and bases in terms of strength, right? We have the same thing for oxidation reduction. We have a table that essentially ranks oxidizing agents, strongest to weakest. And there is a value that's an E naught value for each of these half reactions. Okay. Tell your neighbor why fluorine is the strongest oxidizing agent here and why lithium is the weakest.
Based off of electron. Fluorine. Electronegative.
So fluorine is the most electronegative atom. It has a high attraction for electrons. So it makes sense it would be a strong oxidizing agent that would attract electrons to itself. And lithium, in contrast, it's an alkali metal, doesn't have very many protons in the nucleus, doesn't have a lot of attractive power of the things in this table. Okay. We said previously that oxidizing agents, when they gain electrons, become reducing agents, right? So we can run each of these half reactions backwards, and it would be an oxidation half reaction instead of a reduction half reaction. What happens with the product reducing agent as a function of the strength of the oxidizing agent precursor? Or in other words, how does the strength of the reducing agents on this table, how does it change as a function of where it is on the table? There's a couple of trends here, right? The stronger the oxidizing agent, what does that say about the strength of the reducing agent that forms as a product? The weaker it is, right? Okay, now we can say that from its position on the table, but we don't even have to have the whole table to know, because the numbers for the E0 values tell us something about the strength of the oxidizing agent, and by extension, the strength of the reducing agent that forms. So if you have a large and positive E0 value for the half reaction, for the reduction reaction, what does that say about the strength of the oxidizing agent? It's stronger. Okay. If you have a negative E0 value, what does it tell you about the strength of the oxidizing agent? It's weak, right? But a weak oxidizing agent means something about the strength of the reducing agent that it could form. What does it tell you?
Very strong.
It's very strong. So the stronger the oxidizing agent, the weaker the reducing agent it forms when it gains electrons. And the weaker the reduced, this, why is it hard to have the right word come out of my mouth? The weaker the oxidizing agent, stronger the reducing agent that it forms. Let's be able to correlate that with the E0 values. Okay. These are all E0 values for a forward reduction. Could we extrapolate and say, well, these are all reduction half reactions, but I know all the oxidation half reactions, E0 values. Can we do that? What's the connection here? If we're running it backwards, what happens to the sign of the E0? You just put a negative sign and it flips it. Okay. So this reaction, we did this last class, but tell your neighbor where the equilibrium will lie and how you know. So compare the strength of the copper oxidizing agent stronger plus and zinc stronger.
Yeah.
Copper 2 plus, our starting material over here.
They're both
Zinc
strong.
down here, so which one is stronger?
Hmm.
Copper 2 plus is a stronger oxidizing agent, so where does the equilibrium lie? To the side of product. Okay. Without looking at the position of the table, tell your neighbor how the numbers associated with each of the reduction half reactions for those oxidizing agents, if you had just been given the E0 values without any spatial positioning on the table, how could you use that to identify the strongest oxidant? So the more positive the E0 value for the reduction half reaction, the stronger the oxidizing agent. Which in our table means it's higher up on it. But the real important part is that the E0 value is more positive. Okay. So a student asked this question. What are those numbers, those E0 values? Where do they come from? Okay, when we have a standard table, typically that means that somebody measured them under standard conditions, right? So how were those E0 values that for half reactions measured? Can I measure a half reaction all by itself? You can't have a redox reaction unless something is giving the electrons and something is taking them. So if we have all of these values for things taking electrons They have to be taking them from something that's giving them, right? So these are all measured against the same reducing agent, all of these values. These are the oxidizing agents. They're all measured in an electrochemical cell against the same reducing agent so we can compare them. Just like in a Ka table, we measured all the acids against the water so we could compare them. Here, we're measuring the strength of all of these oxidizing agents against the same reducing agent. Hydrogen gas. Probably, if you thought hard about that, could have figured that out, because what's the E naught value for this reaction? 0. This is reacted. Okay, so all those E naught values for the half reactions come from a specific electrochemical setup where you have a hydrogen reduction, hydrogen oxidation half reaction at the anode. And it uses a special electrochemical cell called the standard hydrogen electrode, abbreviated SHE, that has a platinum wire, so hydrogen gas is filled in as acid, hydrochloric acid or nitric acid. So you have the H plus in solution, the anode, and the hydrogen gas is the electrode. So these values correspond to specific half reactions, but they were actually obtained in a whole redox reaction with hydrogen gas. Okay, so the E naught values mean something for the half reactions. They tell you something about the strength of the oxidizing agent that's being analyzed. Also tell you something about the reaction that occurred in the electrochemical cell with the standard hydrogen electrode. Okay, so if we have a positive E naught value for a given half reaction, what does that tell us about the oxidizing agent? So positive E naught value for a half reaction means it's a decent oxidizing agent, right? But more specifically, it means it's a better oxidizing agent than H plus. Okay. So what's the reaction that actually occurred in the standard electrochemical cell that was used to collect that E naught half reaction value? Okay. We'll come back to that one. We don't care so much about half reaction values, right? What we actually care about is how can we use those E naught values to predict something about an actual electrochemical reaction that we're looking at and that we care about. Because most of the time we don't actually care that much about the reaction with hydrogen. So if we take this value, what we want to be able to do is take a reaction like this one and predict where the equilibrium will lie for that reaction, right? Okay. If we know the delta G naught value, does that tell us where the equilibrium will lie? Yeah. So if we have a negative delta G naught value, where will the equilibrium lie? Right, on the side of product. What kind of E naught value for the reaction would that correspond to? Positive one, right? So how do we take the values on the table and use that to calculate the E naught, not for a half reaction, but for a whole reaction? It's actually as easy as just adding up the E naught values for the two half reactions. Okay, so copper half reaction, that's a reduction half reaction, right? That's the one that happens on the table. So we know that the E naught for that half reaction is just the one that we read off the table. Okay, but the zinc half reaction, that's the one we see on the table. Backwards, right? So we can't take the E naught and move it right off the table. We have to multiply it by -1. when we do that, then that is the E naught value for the oxidation half reaction. When we add the two reactions together to get the product, like the total reaction, all then we have to do is add together the E naught values for the reduction and the oxidation half reactions. Okay, so if the E naught value for the electrochemical cell or for that redox reaction, same thing, if it's positive, what do you know about equilibrium? Lies on the side of product. Okay. I wanted this stage to just point out a place where students tend to stumble a little bit. And they tend to stumble because the textbook loves to hand you useless formulas. Have you noticed that? There's a rule to follow. And the textbook rule says you take the E naught value for an electrochemical cell, take the E naught value for the half reaction, for the reduction half reaction that occurs at the anode. Start with the E naught value for the reduction half reaction that occurs at the cathode. And then the textbook says, and then subtract the E naught value for the half reaction that happens at the anode. Only the textbook is treating them both as reductions, even though it's oxidation that's occurring at the anode. So what they end up doing, when you do it according to their formula, is you take the oxidizing agent, the cathode, the half reaction of the cathode, you read off the E naught value. And you say subtract what's happening at the anode. All they end up doing, subtracting it that way, is flipping the sign. Okay, so you either subtract the reduction half reaction occurring at the anode, or you add them, but you flip the sign for the oxidation half reaction. Those are really the same things. But just be careful that you're not subtracting and flipping the sign. That will not get you the right answer. I prefer to just say, well, what's actually happening? One is being oxidized, one is being reduced. Here's the E naught for the oxidation. Here's the E naught for the reduction. Add them together. Conceptually, that makes the most sense. And it irks me that the textbook could present it in a way that makes sense and instead give you a formula to memorize. Okay. So if we're watching a reaction, what's actually happening? So visualize what's actually happening. If this was all in one pot, could I have a chunk of zinc in a beaker containing aqueous copper 2 ions? If it was all in one beaker, what would you see as that reaction progressed? What you would see is that the zinc concentration would go down, right? And the copper 2 plus concentration would go down. And you'd be producing solid copper and some aqueous zinc, right? In an electrochemical cell, the same thing is happening. It's just they're not all in one pot. So the zinc concentration is going down, right? See that a solid electrode, zinc electrode, is actually being converted. Those zinc atoms are being converted to zinc ion. Okay, what's actually happening is that the zinc is being converted to zinc ion because it's being converted to product, right? Except the increase in product is still at the anode. And the copper 2 plus concentration, what's happening to it? It's decreasing because it's being converted to solid copper. And if you looked at the anode over time, you'd actually see there's less metal at equilibrium that you started with, and the copper cathode would be getting bigger. You're actually converting one to the other. Okay. Ask your neighbor these questions.
Because if this, you would not, we know that.
Okay, the E naught value is 1.1 both.
My understanding.
Rely on the side of solid copper. So we could actually react solid zinc and aqueous copper to produce solid copper. Do that. Okay. What's the E naught for the reaction running backwards? Same reaction, backwards direction. So we take the E naught value and do what to it? Reverse the sign. So for the backwards reaction as written, E naught would be minus 1.10. So if we take that reaction and analyze it, here is our net reaction. This is the reaction that's actually happening in the way that you're used to looking at it, right? You're used to starting material plus starting material reacts to produce product plus product, right? When we put it in electrochemical cell, it looks different, but we still have starting material, reducing agent, becomes product in solution, and starting material in solution becomes product at the anode. Okay, the E naught is 1.1 kilovolts, so we deliver left to right. Set that up away with it. Have it here. We'll have a positive E naught value. Can you see a situation where I give you a reaction, ask you to draw the electrochemical cell for that reaction, and tell me what the E naught value for that reaction would be? Okay. Thinking ahead, if I gave you initial starting conditions, would you necessarily get? So this knot, what does it tell us about the concentrations? They have to be 1 molar of everything in solution, right? A little trickier than that, but the E naught, if everything is 1 molar, then your measured voltage will be the E naught value, right? What are the chances that you're going to set up a reaction and have everything be 1 molar? Pretty low, right? So will we have the E naught value? We won't. Okay. So E naught is directly proportional to delta G naught. They're just versions of the same thing. We can convert from one to the other. A little bit of this last time. Okay. If you calculate the E naught from the table for electrochemical reaction, a balanced reaction, 2 electrons are transferred. How do you tell if 2 electrons are transferred?
Charge.
Well, you balance the equation, and in your half reactions, the total number of electrons given away by the reducing agent is 2, and the total number of electrons accepted by the oxidizing agent. Okay. In that case, our N value here would be 2. In Chem 105, N was an abbreviation for what? Yeah. So, assume that the number of electrons is per mole, there's the number of moles. So if we have 2 moles of electrons, is Faraday's constant. What is that? If we're calculating delta G naught, what are the units we want at the end? Joules. So we have to find some way to translate between measured voltages and joules. And we do it by saying Faraday's constant says this is how much, this big C is a coulomb. Where did you hear the word coulomb before, the name coulomb before? 105, Coulomb's law, right? Named after a guy that did a lot of work with electric fields and charges and attraction between charges. Okay, so there's a unit of charge named after him called Coulomb. Faraday, anyone know who Faraday was? Faraday also did a lot of work. cutting electricity. Okay, so there's a constant named after Faraday, which is if you have a mole of electrons, what's the total charge on a mole of electrons? Well, that's what Faraday's constant is. It's just what's the total charge on a mole of electrons? Okay. If you take Faraday's constant, which is the total charge on a mole of electrons, multiply it by how many moles of electrons you have, then you know how much charge you have, right? The total amount of electrons transferred to charge of them. If you multiply unit of charge in coulombs times the strength of the electric field in volts, what's that the same as? Joule. So coulomb volt is a joule. So this minus NF times E naught is just a way of taking the voltage and converting it to joule. That's all we're doing. Okay, you should be able to do that. So when E naught is positive, delta G naught is negative. What does that tell you about K, your equilibrium constant? Let's be greater than 1. Yeah. So remember, delta G naught negative means equilibrium lies to the right. K value greater than 1 means equilibrium lies to the right. So if you have a negative delta G naught, you have a K larger than 1, which corresponds to a positive E naught value. Okay, how do you keep all those positive and negatives and greater than 1 and less than 1 straight?
Slow.
Jacob says, go slow. If you can connect each of them to what it means for the equilibrium, that will help. Now, the other thing is the equations will help you because you have the equation delta G naught equals minus RT natural log of K. And the math will tell you when K is greater than 1, according to that equation, delta G naught is negative. So that helps you make it. Okay, we also can say when E naught is positive, delta G naught is negative because of reading this equation. So you have the equations to look back to check that your thinking in your memory is correct. Okay. So what I want you to do is connect E and E naught back to delta G naught. They're all kind of the same thing. Okay. So we know delta G naught for an electrochemical reaction is minus NF E naught. And you can do the same thing with that. Okay, so we know delta G naught is just a reference value, right? Delta G naught is just a way of comparing where equilibrium lies for a bunch of different reactions. Now, the E naught comes with everything at 1 molar concentration. That's because if you start at a condition where everything is at 1 molar, the reaction could move in both directions, right? So whatever direction that set of conditions moves to reach equilibrium tells you which way the equilibrium will lie. Okay. So delta G naught is a standard value, doesn't change. What does that say about E naught? It's also a standard value. It's used for comparison. It's the value of the electric potential if everything is at 1 mole, just like it is for delta G naught. Okay. Delta G, does delta G naught change as the reaction proceeds to equilibrium? No, because it's a reference value. And E naught is a reference value and it doesn't change. But what happens to delta G as you approach equilibrium?
Which is 0.
Delta G approaches 0 as you approach equilibrium. And we have those equations that say Q tells you how close you are to equilibrium. And if Q is less than K, delta G is negative. And as Q approaches the equilibrium constant value, delta G approaches 0. Okay, so that means delta G changes with concentration, right? What does that tell you about E? So E changes as the concentrations change as you approach equilibrium, right? When the reaction starts, if it's moving forward, what's our E value? Or the sign of our E value? Positive, and then what happens to it as the reaction approaches equilibrium? It approaches 0. Yeah, exactly. So it's the same, all the same connections as you made in unit 2 and to some extent in unit 3, but we're just translated into electric potential instead of delta G. Okay. Now we had an equation, actually two equations, that pretty much told you how delta G was going to change as you approached equilibrium. This delta G naught is really minus RT, natural log of the equilibrium constant, right? So as your actual concentrations approach your equilibrium concentrations, delta G approaches 0, right? We have a version of that expressed in electric potential instead of Gibbs free energy. We're going to talk a little bit more about that later. One more thing, and then you can break because you're all looking rather pained. Okay. So we're making kind of a concept map here, right? We know that E and E naught are related to delta G and delta G naught, right? And we know that delta G naught is related to K. So could we start with an E naught value and calculate K for a reaction? So if we were doing it with skills that you had previously, we would take our E naught value and convert it to a delta G naught value, and then convert the delta G naught value to a K value. That in your skill window. I mean, on the scale of algebraic manipulations that you have to do in the class, those ones are not the hardest, right? You can do that one. Okay. But somewhere along the line, some physical chemists said, I don't want to do it in 2 steps. I don't want to convert E naught to delta G naught and then convert to K. I want to include it all in one little calculation here. And at 298 Kelvin, they calculated all the different delta G equals minus RT, natural log of K, and incorporated, rearranged and massaged. And just for good measure, in the day of slide rules, took the natural log and converted it to a base 10 log to make it easier. Now we don't care, but historically we have this equation that we can use at 298 Kelvin, 5 degrees Celsius, that allows us to calculate the value directly from the heat. And algebraically, it doesn't get much easier than that. So that's useful. Okay, take a break. Practice those skills.
Yeah, that.
4.924 times 10 to the 137.
Okay. Coming back lecture. Well, that delta G and E, delta G naught and E naught tell you something about the tendency of an electrochemical reaction to move forward under standard conditions. Right, starting from standard conditions. What about if we're not at standard conditions? What then? So from unit 2, what do you know about the direction that reactions proceed? What are the rules? When will a reaction proceed forward? When Q is less than K, right? Okay. So if delta G is negative when Q is less than K, Does that mean that E is positive when Q is less than K? Yes, so an electrochemical cell will proceed forward anytime we're not at equilibrium yet, right? Another way of saying that is to say that the electric potential changes as a function of concentration of starting materials and products. Just like delta G changes as a function of starting material. Or, you can answer the question, what happens to the electric potential as the concentrations change over the course of the reaction? Kind of depends on whether we start at conditions that are to the left of equilibrium or to the right of equilibrium. Let's assume that we start at non-standard conditions. We don't have enough product yet to be at equilibrium. What will the sign of E be? We don't have enough product yet. That means Q is less than K. What will the sign of E be? It'll be positive. So what will happen to the reaction? We will continue to convert starting materials to products until you get to equilibrium. As that happens, what happens to the measured electric potential? It goes from positive and it gets less and less positive until what? It reaches equilibrium where it's 0. Absolutely. Okay. Now for unit 2, we talked a lot about equations that correlated what happens to delta G as a function of the reaction quotient Q, right? Which is just a mathematical way of saying what happens to delta G as the concentrations change, right? Okay, we have an equation that says the same thing, but for electric potential instead of for delta G. Okay. So we have this equation, delta G equals delta G naught plus RT natural log Q, right? Which we could also express this way. Which essentially told us that anytime Q is less than K, or in other words, anytime we don't have enough product yet to reach equilibrium, then delta G will be negative and the reaction will proceed forward. Okay, but we have a mathematical relationship between delta G and E, between delta G naught and E naught. Okay, so we're going to take these versions of delta G and delta G naught and lift them into the equation that you knew already. Then what's going to happen? It's mathematical massaging, right? And when you're done with the mathematical massaging and simplifying, we have an equation called the Nernst equation. Now, this is the fundamental form of the Nernst equation. If we're at 298 Kelvin, then we know what the temperature is, and R is a constant. So we can take that RT and Faraday's constant. If we take all the constants here, we can convert it into this equation. Okay, so these two equations are just forms of these equations that you already know, but expressed in terms of electric potential instead. Which begs the question, are these named equations? And that Hopf equation, and then we have the Arrhenius equation, and we have a couple equations that have names, right? This one doesn't have a name. Why does this one have a name? The Nernst equation actually came first. Electrochemistry was understood and studied long before entropy was even evaluated. Okay, so these are both called the Nernst equation. Just for yucks, turn to your neighbor and say Nernst 15 times as fast as you can. Aren't you glad your last name isn't Nernst? Yeah. Okay. So this one here ends up being the one with most of the time, because most of the time we're dealing with room temperature reactions or 298 Kelvin. Okay, so put your math hat on. What does this relationship, this mathematical Nernst relationship, tell you about what happens as you approach equilibrium? How about we just say that it's when the concentrations change, when they're not standard concentrations, what happens to the voltage, the electric potential?
Changes.
It also changes. Yeah. Okay, here's some student questions. One says, I don't understand when we use the Nernst equation. Tell your neighbor when you think you will use the Nernst equation. Connect it to delta G equals delta G naught plus RT.
It sounded good. It sounded like.
I guess.
Super good.
Yeah. what-
It makes sense. Q. Approaching equilibrium.
So the E naught for an electrochemical reaction will tell you what will happen to that reaction when you're at standard conditions. How often are we really at standard conditions? Not all that often, right? So when we actually set up an electrochemical reaction at the concentrations that we have in solution, which are rarely 1 molar, let me tell you, 1 molar is way concentrated. These equations allow us to predict the actual direction of the reaction and what's going to happen at the concentrations that we have. So in practice, these are the important relationships. These are the important equations to say, for the conditions that I actually have, what's the electric potential and how will the reaction happen? Okay. So one way that the Nernst equation can be read is it expresses what you already know, which is electric potential approaches 0 as the reaction approaches equilibrium. Okay, so take this reaction here. Question. Is this different than what you've done before? So here's our electrochemical reaction. Here's our Q value. It says, here's a question. There's some reagents missing in this Q expression. Why am I only using that Q? Why does the Q expression only use the aqueous reagents?
I was gonna say because the other ones are solid.
Because the other ones are solid. Exactly. So Q here, our zinc electrode at our anode and our copper electrode at our cathode, they're solid, so we get to leave them out. Which every time I get to leave something out, I'm really happy. Okay, so in this case, if it's a 298 Kelvin, here's our Nernst equation. Our Q value will just be the ratio of our zinc concentration to our copper. Or zinc ion concentration. Notice anything mathematically about this? If our zinc concentration, if our zinc ion concentration and our copper ion concentration are the same, what is our measured voltage? Okay, if in this case, all of our stored geometries are 1, so in our Q expression, there's no exponents, right? If my zinc concentration of the ion and my copper ion concentration are the same, what's my Q value? 1. When my Q value is 1, what's the value of base 10 log of 1? 0. So what is my measured electric potential? Equal to the E naught, which is actually pretty useful to know. So whenever our Q value is 1, our E value equals the E naught L. So when we're doing an electrochemical reaction in an electrochemical cell, can we get the E naught for the redox reaction without being at 1 molar? Yes, we can. So, okay. If we look at that equation, when Q equals the K, you end up with E equals 0. And anytime Q is 1, which in this case happens when all the concentrations are equal to each other, then E equals E naught. Let's go through some of the pre-lecture quiz. So here's one. So we have an electrochemical cell, which based on oxidation of zinc metal and the reduction of silver 1 ions. Okay. From that first sentence, can you construct the half reactions? Yeah. So if we say we have the oxidation of zinc metal, that means zinc is oxidized to produce zinc 2 plus and 2 electrons. Now, if you're completely at sea and the terms oxidation of zinc metal is making you hyperventilate, is it totally acceptable to say, I'm just going to look at the table of reduction potentials and see what happens to zinc when it gets oxidized? Yeah, you can. So you can read these half reactions off of the table. Okay. The reduction half reaction for silver ion demonstrates that it's just silver plus. So each silver atom takes 1 electron. Tell your neighbor why we have to have stoichiometries of 2 in front of every silver when we don't have to have those stoichiometries of 2 according to the Chem 105 balancing rules. You understand my question? In Chem 105, we told you that conservation of mass, the conservation of the numbers of atoms, determines how you balance a reaction, right? According to that rule, we don't have to put a stoichiometry of 2 in front of the silvers. Why do we have to here?
We have 2.
Yeah, there's 2. Every time one zinc atom gets oxidized, it gives away 2 electrons. Which means every time one of these oxidation half reactions happen, we have to have 2 half reactions of the reduction half reactions happening to take those electrons. So when we balance it so the number of electrons donated by the reduction, the number of electrons donated by the oxidation half reaction is the same as the number of electrons gained by the reduction half reaction. In this case, the lowest possible number we can get is 2. What's our N value for number of electrons? It's 2. Yeah. Okay. So how do we translate that to our electrochemical cells? Well, we say oxidation occurs at the anode, reduction occurs at the cathode. So we take our oxidation half reaction. So this side is zinc. Well, and this side is the silver. Okay. If we've constructed our electrochemical cell appropriately, what should the sign of the E value be? It should be positive, right? Okay. So that means electrons should flow from left to right, or from the strongest reducing agent here, which is zinc, to the strongest oxidizing agent, which should be locate the silver nitrate solution on the diagram. We'll put our half reactions in because they told us which half reaction goes at the anode and which goes at the cathode. So where's the silver nitrate solution? It has to be in solution at the cathode. So our half reaction, we have aqueous silver ion, which has to be in solution. And we have solid silver, which is typically at the cathode. We have that electrochemical cell corresponding to that reaction. So the question says, if I start with a half molar solution of silver nitrate, which is cathode, and a 1 molar solution of zinc nitrate, what's the reaction quotient? Are we at standard conditions here? We're not. We need to know what the reaction quotient is. The trick is you have to keep straight what's your product and what's your starting material in order to calculate your Q value, right? So for me, that always works the best to say, here's my half reaction, here's my net reaction. When I have that reaction, now is it hard to keep track of what's starting materials and what's products? No. Okay. So Q value, you just say zinc is my product, zinc ion is my product, silver ion is my starting material. What do you have? Classic electrochem Chem 106 blender. What do you think it is? Not square unit. And it's because very often in redox reactions, all the stoichiometries are 1. And you forget that you have stoichiometries that are non-unity. And you have to include them in your Q value. I would guess probably 40% of you did this problem correctly, except forgot to square it. Okay. When you do that, when you square it, because it's not 2. Okay. So we take that electrochemical cell with the concentrations that they give us, and we say, if you run the reaction at 290 K, what will the measured voltage be? So we carefully had you say, what's the reaction? Set up your electrochemical cell, define Q. Have this equation that allows us to predict what the measured voltage will be, right? We know what our Q value is, it's 4. What's our N value in this equation? 2, yeah. So what we then need is our E naught value. Always, it's easiest if you just systematically work every redox problem to say, what's the reaction that's happening? What's the oxidation half reaction? What's the reduction half reaction? What are the E naught values associated with those half reactions? And add them up. Okay. If you add them up, that tells you, calculate what your E naught for your reaction is, which tells you this. That also tells you your N value, right? Because you can look at it and figure out what that balance or geometry is. Okay, so we calculate the E naught value by saying this zinc reaction, that's an oxidation half reaction. So we're going to run the zinc reaction backwards from where it is on the table. So we take the E naught value, multiply it by -1. With a negative E naught value, so we end up with a positive. The silver half reaction, we pull it right off the table. The direction is on the table because it's a reduction half reaction. We take the E naught value right off the table, add them up. Now we have all the information we need. Plug into the Nernst equation. Add those values in, 1.54 volts. Okay, what's the relevance of 1.54 volts? What direction is this reaction running at the moment of those concentrations?
Forward.
It's still going to run forward. How far from equilibrium are we here? Actually pretty far from equilibrium. The E naught value here is 0.56. That's a pretty positive E naught value for the reaction, which means equilibrium is pretty far to the right. We're not anywhere close to that. Okay. If you can explain to your neighbor how you would do this one.
So.
Okay, so we're gonna have to use the Nernst equation, right? Time you're calculating the electric potential at non-standard conditions, you're gonna have to use the Nernst equation, which means you have to calculate E naught. You have to know what the number of moles of electrons transferred in is, what Q is to plug it into the equation. Do we actually know at this point what the concentrations are to plug into Q? That's the only thing we know. We know the change. Question is that change from the reaction moving forward, or is that change from the reaction moving backwards? How would we know? Say it again.
The reduction table.
Okay, we start at standard conditions, right? Which means the E naught value tells us what direction the reaction is going to proceed when we're starting, right? So if we know the E naught value, then we know whether the reaction is moving forwards or backwards. And from that, we can figure out what the concentrations are that we actually have. Okay, so the E naught is 1.104 volts, right? We have our Nernst equation. We know that this is how we define our Q value, and we know that our N value is 2. When the reaction starts at standard conditions, as soon as we turn on the electrochemical cell, what direction is that reaction going to proceed? Are we moving forwards or backwards? Forwards. Okay. So if we're moving forwards, at the time point that we're asked about, what's our concentration of copper ion and what's our concentration of zinc ion? If the reaction is moving forward, then zinc, what's happening to the concentration of zinc ion? Decreasing because it's getting used up. And what's happening to the concentration of zinc ion? It's increasing because it's being produced, right? So the zinc concentration at the time point is the starting concentration, which is 1.0 molar, plus the change, which they gave us. Our concentration is 1.35 molar of zinc. What is it of copper? 1 molar minus 0.35 or 0.65. Okay, now do we have everything that we need? We do. We know our Q value is 2.08. Plug the E naught value that we have into here, the N value of 2, value that we calculated at 2.08, we end up with a value of 1.095 volts. Okay. Is the reaction at equilibrium at this point? Ben says no. Justify your position. We're not at 0, right? So are we at equilibrium? No. Are we to the left or the right equilibrium? Right. Which way does the reaction still have to go? It has to go forward, so we're still to the left. Okay. Reaction is still continuing. Okay. Is this fundamentally different than what you did in Unit 2? It isn't. It's just that you have to step back a bit, construct your half reactions, get your E naught value, figure out where you are with the electrochemical reaction. And then the analysis is pretty much the same as Unit 2, except we're plugging it into the Nernst equation instead of into a double chain. Okay. Here's a question. So this one, we have a zinc half reaction and a silver half reaction. When we construct the reaction, we get this. And we know the Nernst equation. Okay, when will the E value be equal to the E naught value? Well, let's just evaluate each of these. When Q is K is equal to K. When Q is equal to K, what do we know about that reaction? It's an equilibrium, delta G is 0 and E is 0. Now, is it likely that each cell is also 0? Probably not. Probably not. Okay. How about when the measured voltage in an electrochemical cell housing the redox reaction is 0? What is that describing? That's describing equilibrium, right? Now, unless the E naught happens to be 0, and E doesn't equal E naught there. Okay, how about at the instant a reaction in an electrochemical cell containing 1 mole of dissolved ions begins? Is that a description of a standard set of conditions? Yeah. So the measured E naught is, measured electric potential E is E naught if you start with all 1 molar. Now, as soon as you turn it on, you're at E naught. After a millisecond, are you at E naught anymore? How come? Change the concentrations, you're no longer at 1 molar anymore. You're not under standard conditions, so now you're okay. How about D? At the instant of reaction containing exactly equal concentrations of dissolved ions begins. Careful. What is our Q value here? When we have exactly equal amounts of dissolved ions for this reaction, will our Q value be 1? In order to get our Q value, we have to square our silver concentration. So that rule about exactly equal concentrations of dissolved ions, that only works when the stoichiometry is 1 for everything. Because you only get a Q value of 1 at equal concentrations. If you don't have to square or, what do you call it? Cube anything. So that rule about exactly equal ion concentrations only applies if the Q equals 1 at those concentrations, which only works if all the stoichiometric coefficients. Okay. So the only answer was C. Yeah. Okay. Now let's look at this example. Tell your neighbor which 1, 2, and 3, and whether you actually have to calculate anything to know those answers. So this is the same reaction, right? These are identical electrochemical cells, except for what?
Right.
At the beginning.
Except for the concentration of the dissolved ions in solution at the anode. and
0. It's the same as the other
Okay.
first one.
If we
That's
wrote
what I
a
would
balanced
think, too.
reaction for both of those electrochemical cells, that's what it would look like, right? Same reaction. Stoichiometric coefficients for the dissolved ions. 1. Okay. So what is our Q value for the top reaction? Q is 1. Okay. So at the moment the reaction begins for this top electrochemical cell, what is your value for your electric potential? It's whatever your E naught value is, right? Okay. Now for the bottom one. What is the Q value at the moment that reaction begins? It's also 1. So those two electrochemical cells are going to behave the same way. They'll have the same measured potential throughout. Okay, so for both of those reactions, because stoichiometric coefficients for all of the dissolved ions are 1 and the Q values are the same, both of those have Q values of 1 at the moment the reaction begins. So for both of those electrochemical cells, the E value at the moment the reaction begins is the same as the E naught value. Okay. What will E be when the reaction reaches equilibrium in each case? 0. Yeah.
Nice.
Okay, so we talked about all of this. You may want to go back and make all those connections explicit for yourself after class. Okay. What if, can we run an electrochemical cell that has the same half reaction on both sides of the reaction? Actually, you can. Okay. What is E naught? This is our this is our reaction, right? Can you get a voltage out of setting up an electrochemical cell that way? What will our standard E naught value be? Okay. Look at what the equations tell us. When we calculate our E naught value, we have the same half reaction for the oxidation and for the reduction, right? So the half reaction, tell your neighbor what the oxidation reaction is. Half reaction. Oxidation half reaction, gaining electrons, right? So that would be copper 2 plus gains 2 electrons to become copper solid. And say that backwards. I think I said it backwards. Okay, let's start with the oxidation half reaction. What's losing electrons here? Copper solid, that's your starting material, is losing electrons to form your copper 2 plus as a product. So your oxidation half reaction is copper solid goes to copper 2 plus 2 electrons. Your reduction half reaction is copper 2 plus goes to gains 2 electrons to form solid copper. Okay, E naught for each cell. It has to be 0. How come? Because it's the same half reaction, run forward and run backwards. When you add the two together, you can take the E naught value for the forward reaction, add it to the E naught value for the backwards reaction, which is the same number, just negative, and the sum is going to be what? 0. So E naught for these electrochemical cells is 0. So does that mean that E is 0? It doesn't, because whether E is 0 or not depends on the value of Q. So we have to figure out what the value of Q is for those two electrochemical cells, and then use that to figure out what the E value is. Okay. Classic. All right. E naught is 0, right? So we can go back to our Nernst equation and leave out the E naught value because it's 0. Which leaves us with the equation, electric potential of the cell under those conditions is just whatever your Q term would give you. Okay. What's our N value here? It's 2.
It's 2.
It's 2. Maybe if I draw it out. Okay, so what we have here, copper 2 plus gains 2 electrons, form solid copper. Solid copper loses 2 electrons. Right? Okay. How do we decide what's starting materials and what's products here? What is the E naught value for copper 2 plus? 2 plus gaining electrons. 4. When we do the backwards reaction, get minus 3, 4, so 0 volts, right? Okay, let's construct the electrochemical cell, because I think that will be helpful. This. So our electrochemical cell, let's do the top one. Our shorthand goes like this. Okay. So in our electrochemical cell, that's a pretty minimal electrochemical cell, right? We have copper 2 plus in solution here. Copper. This is copper. Copper 2 plus. All right. Which half reaction goes where? So the anode has oxidation occurs at the anode on the left. So the half reaction here is copper solid becomes copper 2 plus 2 electrons. And at the other side, we have copper 2 plus 2 electrons. Copper solid. All right. What is the concentration of copper at the anode? That's the one that you read off of the left-hand side. So that's 1 molar. And the concentration at the cathode is 0.01. What's the Q value? This is the tricky part because the Q value, copper ion divided by copper ion, which concentration goes where? Okay. If it's constructed this way, which copper solution is going to increase in concentration and which one is going to decrease in concentration? Think about the electrochemical cell. What's happening at this electrochemical cell?
More copper.
Yes, oxidation occurs at the anode, which means copper solid is oxidized to produce copper 2 plus ion, right? So the copper here at the anode is increasing in concentration. What does that mean about whether it's a product or a reactant? So the oxidation half reaction has copper occurring as a product, right? So that means the copper in solution at the anode is the product. Okay. When the electrochemical reaction is proceeding, electrons are traveling through the wire. Where do they go? They go down through the copper electrode. And then they meet the copper ion in solution and react with it to form copper solid. So this copper 2 plus starting material or product? It's starting material because it's getting converted to solid copper. So here, starting. Okay, so now go back to this Q value. This is copper ion of the product divided by the reactant. Another way of putting that in terms of the electrochemical cell is to say that we have in the numerator of our Q value is the ion concentration at the cathode. Because that's the one that is, no, I had that wrong, don't I? I wrote it wrong. Okay, the product is the one that's increasing in concentration, right? Where is the copper ion concentration increasing? At the anode, right? So we can write the copper concentration at the anode as the concentration, as the product concentration. And the copper ion concentration at the cathode. Okay, now we can go back to our electrochemical cell. What's our Q value? Q value is the concentration at the anode, which is 1 molar, divided by the concentration at the cathode, which is 0.01 molar. So what's our Q value here? Value is 100. Okay, so the hardest part about this problem is just figuring out and keeping track of which concentration goes in the numerator and which goes in the denominator. If you go back and you say, which one is increasing, that's the product. Which one is decreasing, that's the starting material. Yes.
Could you also just look at the like simplified version and realize?
Yes, you can. Good connection. Okay. The shorthand for the electrochemical cell, does it define starting materials and products for you? It's written, starting material goes to product, starting material goes to product. So you could have skipped all of that analysis, although it probably was helpful to make the connection. You could skip all that analysis and just say, well, 1 molar has to be the product. 1 molar has to be the starting material. Okay, so the top cell, you calculate minus 0.0592. What does that value tell you? That reaction would actually move, is moving backwards. The bottom cell, you get reverse value, which is 0.0592 volts. And for both of them, when they reach equilibrium, what would they E0? What do you know about the final concentrations when they reach equilibrium? So intuitively, what do you think the concentrations will be at equilibrium? The same. Once you get the same concentration at your anode and cathode solutions, then once mathematically and then intuitively, when the concentrations become the same at the anode and the cathode, what will your Q value be? 1. So what will your E value be? Equal to the E naught, but what's our E naught here? 0. So equilibrium happens when the concentrations are the same at both sides. Intuitively, does it make sense that if the concentrations are the same at both sides, and the 2 sides are identical, there's not going to be electron being transferred one way or the other because the sides are the same. Yeah. Okay, so here are equation summaries. Calculate the E naught for a cell by adding up the standard the standard potentials for the half reactants. Add up the reduction and the oxidation. Connect the E naught values to delta G naught values by extension to K. Same for E values. And we can calculate the K values from the E naught values. And we can calculate the E at non-standard conditions using two different versions of this equation. A couple of examples of using the next equation. Not the version that I 11 and 12. I just want to talk about one more thing before we end. One of the cool things about electrochemical cells and redox reactions is that they provide the only way in which we can actually make a reaction move backwards. So normally in an electrochemical cell, which way do electrons flow? They flow anode to cathode or left to right, or from the strongest reducing agent to the strongest oxidizing agent. That's essentially the way that they go. Okay, but what if we change the voltage across the wire between the anode and the cathode by hooking it to a larger current? We can actually use electricity to pump electrons from the cathode back to the anode, which in practice means we can force electrons to move we can make electrons go in the direction of a reaction from the weaker reducing agent to the weaker oxidizing agent. So we can make a reaction go backwards. Okay, so if you pump electricity in, you can make the reaction go backwards, because it's all about the flow of electrons, right? There's a spontaneous direction that the electrons want to go. So because of we have access to electricity, we can actually pump things backwards. Okay. Which means you can run a reaction against its spontaneous direction. Does that violate the second law of thermodynamics? So normally we say reactions occur in the spontaneously in the direction of a negative delta G, because that's the direction of a spontaneous reaction that increases the entropy of the universe. And that's because negative delta G corresponds to a positive delta S in the universe. When we incorporate added electricity, we're adding entropic considerations that come from generating that electricity and heat being generated from that, so that we can still make it happen. We're just increasing what the system is, essentially. Okay. Means is we can actually make redox reactions like that without changing the concentration, just by pumping electricity into them. That process is called electrolysis. So anytime we take a redox reaction and pump electricity in it in order to make it go backwards, that's called electrolysis. Okay, so here's an example. Which one of those is a spontaneous direction? Tell your neighbor which one you think is spontaneous and why. So chlorine is a much stronger oxidizing agent than Na plus, right? So this bottom reaction is the one that's spontaneous. In fact, it's so spontaneous that there pretty much isn't any chlorine gas naturally available anywhere. And there isn't like a mine where you can mine solid sodium, because all the sodium in the world exists as Na plus pretty much. And all the chlorine in the world has oxidized something and that now exists as chloride. But all of you in Physical Science 100 or in high school watched somebody do a demo where they had a chunk of solid sodium and they cut it and added a little piece of water and it did it all, right? So there is solid sodium somewhere. And if you're like me and you worked summers as a lifeguard, you saw big tanks of chlorine gas that were used to chlorinate pools. Where did the chlorine come from? And where did the sodium come from? And Jacob says the first reaction. So all that chlorine that chlorinates pool water and all the sodium metal that's used for stuff is most likely created by electrolysis of the sodium chloride solution. Or take a bunch of seawater, run a whole bunch of current through it, and end up producing solid sodium and chlorine gas. Okay, so here's an example of a way that people would create chlorine gas and solid sodium. And they essentially run at the anode. They're running an oxidation reaction that shouldn't actually happen, but they make it happen because they're pumping an external source of current and voltage that pumps the electrons in the oxygen. Okay, so let's talk practical applications. Electrochemistry was actually discovered via technology before science. So people were using electrochemistry and redox reactions to do stuff with technology before the chemists and the physicists really even understood what electrons were or how things work. Okay, here's one. What's a battery? So a battery is really just a mini electrochemical cell. And it's set up with the anode at one end and the cathode half reaction at the other end. In between, there's a bunch of electrolyte, which just means dissolved soluble salts. It acts like the salt bridge. So a battery is a little electrochemical cell with an oxidation half reaction at one end and all the chemicals that that needs, and a reduction half reaction at the other end. But it's not hooked to anything. There's no wire connecting the anode and the cathode. How do you connect anode and cathode for a battery? Let me say it louder.
You plug it into something?
You plug it into something. When you put your battery into a device, the device closes the circuit and essentially makes the wire between the anode and the cathode. So as soon as you plug your battery into something, you just started your redox reaction. And as long as the redox reaction hasn't reached equilibrium yet, what happens to the current? Yeah, you have a current. Okay. What happens when the redox reaction contained in the battery reaches equilibrium?
Stops.
The battery's dead, right? The electric potential is zero, no more electrons travel through the wire, no more current. In practice, when we say the battery is dead, like I just had what I said was a dead battery in my microphone. Was it really dead? Was it really all the way to equilibrium? So what happens to the flow of electrons or the electric potential as the redox reaction proceeds towards equilibrium? The voltage diminishes, right? When the voltage drops below that, what the application you're using it for needs, then your device stops working. And we say, oh, the battery is dead. Is it really all the way dead? Probably not yet. But it's nearly dead. Okay, so what does it mean when a battery is dead? Tell your neighbor.
Very close to it.
This is an opportunity for it right here. Mostly dead and all dead are not the same. So what we call a dead battery is mostly dead. It probably hasn't completely.
I mean, a stronger battery or a battery that lasts longer has concentrations that are so far left of equilibrium that they can go for a while.
Yeah, did everybody here take a question? So a battery that's longer lasting has higher concentrations of starting material.
So like a lithium battery just has like, why is it called a lithium battery?
I think it's called a lithium battery. One of the half reactions includes lithium. Yeah. Okay, what happens when you recharge your battery?
Doing the electrolyte.
So you take your phone out and you plug it into current. What is the current doing when it flows into your phone? It is doing electrolysis. It is reversing the reaction. So when your battery is being used and running your phone, starting material was being converted to product, right? When enough starting material has been converted to product, the voltage drops enough that it doesn't work anymore. So in order to recharge your battery, what do you do? Plug it into power, what does it do to the redox reaction? Takes those products that you made, converts them back into starting material, so then your battery works again. Let's see. Okay, in terms of the Nernst equation, when you recharge your battery, what's happening? So when we get to E cell is close enough to zero that it's not charging your phone. When you plug it back in, what happens to Q? Q goes down. So first say, over the course of the reaction, as the battery is being used up by running your phone, what happens to Q? Okay, Q is products over reaction, so Q gets bigger. When Q gets bigger, this whole term gets bigger. It's attracting that bigger term, so what happens to your cell? Okay, when you recharge your battery, what happens to Q? You're making starting materials again, so Q goes down. When Q goes down, so you're restoring the voltage that your battery can exert, which allows it to generate current. Okay, one more final thing. Should have worn my inexpensive gold-plated earrings. So you can buy solid gold jewelry, or you can buy gold-plated jewelry. How do they plate things? That's just a redox reaction. Attach a wire to the jewelry, plop it into a solution of aqueous ions. You run a current through the wire. The current runs through the jewelry, makes it act like the cathode, and plates out the aqueous metals onto the jewelry. So that's all you're doing. I want to silver plate a spoon. Take some inexpensive, not expensive spoon, attach a battery or electricity to it, plop it into a silver ion solution. Electrons will run through the wire down through the spoon, acting just like a cathode. Those electrons meet the silver ions in solution, convert them to solid silver, which then deposits. That's all you're doing. So you didn't know that electrochemistry actually. Okay, that's the end. For exam, if you can think through and understand and analyze what we did in the pre and post lecture quizzes on both of the recitations and the questions in class, I will not throw something different than that. If you are comfortable with all the things that we've done.
At the same time, right?
A level of automaticity is helpful here because there are lots of places to just flip a sign, put your anode and cathode in the wrong direction. There's just a lot of fiddly places to make a mistake. So make sure that you're comfortable enough with it that you don't have to think so hard.
Dr. Ackroyd. Like, the exam, just the.
I have
normal-
office hours on Monday from 12 to 1:30, and I'm just gonna be hanging around, so if I'll be there before office hours and I'll be there after office hours. So if I make office hours, stop by. So I view review.
Friday.
Yeah, there's no school Friday. One Wednesday.
Oh, and by the way, I changed the recitation deadline to Friday. I had some feedback from students that they really wished that the reading quiz was due on Thursday and the recitation was due on Friday. I switched that for today, except I actually made the quiz due tomorrow too, because why confuse things? Yeah. I don't want to.
This is right.
Yes.
No, I need to take physics. You should take physics.
I think so. I might do, I don't want to take science classes at the same time, so I might do, semester.
No.
What do you wrote, I think is.
I think that there's a three. I think they're all.
It's like, okay,
He's
I'll make sure it's not.
Such a nice individual. Super smart.
Part of my life.
Honestly, it's a real.
I didn't figure this out.
It's helpful, but sometimes
Oh, crazy. But like, it helps because they're different, you know, it's a different type of. Thanks so much. I'll go.
Mine, I literally said, I'm putting in my noise canceling headphone. Like, possible.
I'll try it.
sometimes means that people stop as soon as they get to 90 and miss it. They could have had that. wouldn't
Most
have
of the time it's good, except questions like that. I'm like, I have no idea what's going on right now. So,
I'll look at that again if you want to come to office hours.
okay, yeah, I might run by. Might as well learn something. I want to learn how to do it.
Approach a question on the exam.
Dude, that's like so many concepts together. That's like 1,000 concepts. I know, maybe it might be good to learn. Thanks so much and have a good weekend.
Question. So the reason electrolysis doesn't violate the second law of thermodynamics is because it's entropically favored.
Thank you. Thanks, Dr. Ackroyd.
So it's the total entropy change that matters, right?
Yeah.
Normally, we look at the reaction and the system and the surroundings, right? If you're forcing electricity through, then the system includes everything that you needed to generate that electricity and all of the heat of everything running through the wires. And, then the delta G of the reaction doesn't include everything else that matters.
Okay.
So we can run a reaction in a direction that is prohibited by the negative delta G because we're actually talking about more stuff than just that, right? It's the same question of how can we freeze ice in a freezer? Like the freezer in your house is at 25 degrees and ice shouldn't freeze at 25 degrees, right? But we're messing with the system because we're running electricity into the freezer and it's kicking heat out the back vent of the freezer. And it's not just about the ice cubes anymore.
Okay.
Does that make sense?
Yeah.
And it's the same thing with this.
Gotcha. Cool. Thank you.
But it's kind of cool that this is the only situation where we can say, I don't care what delta G says, I can do whatever I want.
Right. That is super interesting.
Every time you plug in your phone.
There you go.